Hello everybody. In this video, I'm going to be talking about homomorphisms and isomorphisms. So these are like the analog of continuous functions and topology to abstract algebra. And for each structure, algebraic structure that we define, there's going to be a notion of homomorphisms and isomorphisms. So of course, we're just going to look at the group homomorphism definitions. So I want to remind you, before we get into these, of some properties of functions, and these don't have to be in from group to group or anything like that. These are just the functions from one set to another. And these are injective. So if we have a function f from a to b, it is injective if f of x equals f of y implies x equals y for all x and y in a. A function is surjective if for all y in b, there is an x in a such that y equals f of x. And a function is bijective, or it is a bijection. Both are true. So it is injective and surjective. And at least in the case of finite sets, if you have a bijection between two finite sets, that means that the two sets have the same cardinality. They have the same number of elements. And the same kind of idea extends to finite or infinite sets. So there are infinite sets for which there are bijections between them, and there are infinite sets for which there are not bijections between them. And so this idea allows you to distinguish between different types of infinity. Of course, that's not really what we're talking about. There's also some notations that I'll remind you of. The image, f of a, is the set of y in B such that there is x in A with f of y equal f of x. Right? So in particular, a function is surjective if its image equals B. And you can always restrict a function to be surjective by saying f goes from A to f of A. And then there is the inverse image if S is a subset of B, f inverse of S is the set of x in A such that f of x is in S. Okay. Pretty standard stuff. So with this in mind, we're going to move on to what homomorphisms are. So a map from one group to another is a homomorphism, and I'm going to be abbreviating this obviously by hom, because I don't want to write homomorphism all the time. And the definition is actually very simple. all that we require is that, and actually I'm going to start using implicit multiplication here. All that we require is that if there is a multiplication inside the function, we can break it up into a multiplication outside the function. So here, x and y, these are being multiplied in the g operation. And then f of x and f of y are being multiplied in the g prime operation. Okay. So the first proposition is that the image of the identity of G is equal to the identity of G prime. And the proof is fairly simple. It's almost like the identity is unique proof. Well, I guess not really. So what we do is we start with f of e, and e we know is equal to e times itself. And then when we have a product inside of a homomorphism, we can split it up into a product of the function values. And so by multiplying by the inverse on both sides, we get that f of e equals e prime. Right? We multiply by the inverse of f of e. So essentially, homomorphisms preserve the identity. Now, it may be the case that you can have non-identity elements in G which map to the identity in G prime, but we'll get to that in just a bit. The next proposition is that homomorphisms preserve inverses. In other words, f of x inverse is equal to the inverse of f of x. And the proof is also fairly simple. We use this breaking up technique. So e prime is equal to f of e, as we have proved. And e is equal to x times x inverse. And we can split this up into f of x times f of x inverse. So we can see that f of x and f of x inverse are inverses in G prime. And these propositions prove that f of G, the image of G, is a subgroup of G prime. Okay, and just to remind you, or if you're watching this video without watching the others, I'm using this notation. I don't think I've ever seen it, but I'm just using it to save time. This, I'm just writing a subgroup. It's just a notation that means f of G is a subgroup of G prime. Okay. The next thing we are going to look at is the kernel. The kernel of f is the set of x in G such that f of x is equal to the identity in G prime. Okay. And as another basic proposition, we're going to prove that Ker f is a subgroup of G. So proof is fairly simple. So we have to show, so let's let x, y be in the kernel. Then we have to show that x times y is in the kernel. So f of xy is f of x, f of y, which is e prime, which is e prime. So xy is in the kernel. Oh, and this is also, you can write this as the inverse image of the set containing the identity of G prime. Okay, now we need to show that E is in Ker F. And of course, this is just because f of E equals E prime, which we've already proved. And then we need to show that X is in Ker F, then f of X inverse equals the inverse of f of X, which is f of X is E prime, and then the inverse of the identity is the identity, and so this shows that the inverse of X is in the kernel of F. And so these three properties show that the kernel of F is a subgroup. All right. The next thing we're going to prove about the kernel is that, lost it. Oh yeah, the kernel of F is equal to just contains the identity if and only if F is injective. So here we have, for homomorphisms, right, and I haven't been writing it, but here F is always going to be assumed to be a homomorphism unless otherwise stated. So here we have a way to, right, injectivity is a completely set theoretic idea, and we're relating it to a group theoretic idea. In the case of homomorphisms, of course, but this is a powerful thing. So the first direction, right, so I'm going to denote it like this, right? We're going to be assuming that the kernel of F is trivial. That's what we say. The kernel of F is trivial. So to start, right, we're going to prove that F is injective, right? So we start with f of X equal f of Y, and then we can multiply by the inverse of f of Y on both sides. And then since homomorphisms preserve inverses, this is the same thing as f of X times f of Y inverse equaling E prime. And then this is the same thing as xy inverse equaling E prime. Now this means that xy inverse is in the kernel of F. And since the kernel of F is just trivial, we have that xy inverse equals E, and therefore x equals y. And so that proves that f of X is injective, or F is injective. Now in the other direction, we start with assuming F is injective, and then we prove the kernel of F is trivial. So let f of X, or I guess I'll say let X be in the kernel. Then f of X equals E prime, which equals f of E, right? We know that E is always in the kernel. And since F is injective, f of X equals f of E implies X equals E. Thus, the kernel of F is just trivial. Okay. So now the next thing we can prove about homomorphisms in general. If H prime is a subgroup of G prime, then the inverse image of H prime is a subgroup of G. Okay. So I'm just going to assign a letter to the inverse image of H prime. I'm going to call it H. And so we just have to prove the different subset or subgroup properties. And so if x and y are in H, then f of xy is f of x, f of y, and this is in H prime, since H prime is a group and f of x and f of y are in H prime, right? The product of two elements in H prime is going to be in H prime, and so this shows that xy is in H. E is in H because f of E is E prime, which is in H prime. If finally we have to show that inverses of elements of H are in H. So we just take f of x inverse. This is the inverse of f of x. And this is in H prime, since f of x is in H prime. Thus, x inverse is in H. Okay, so essentially, every step of the way, we're using the properties of H prime and just translating those back to H. Another important thing, if f and g, or let me write it like this, if f is a homomorphism from g to g prime, and g is a homomorphism from g prime to g double prime, then I'll specify that these are homomorphisms, then H, which is equal to the composition of G of f. This is a function from G to G prime, and this is a homomorphism. And the proof is just fairly straightforward, right? We start with a product of elements in G. This becomes a product of elements in G prime. And then this becomes a product of elements in G double prime. It's a very simple proof. Now we get to an isomorphism. A bijective homomorphism is an isomorphism. In this case, f inverse is also an isomorphism, right? So whenever you have a bijective function, you can define an inverse function. And if your function is an isomorphism, meaning it's bijective, you can define an inverse. And if it's a homomorphism, then this inverse will also be a homomorphism. And since it's bijective, it'll then be an isomorphism. Okay. The last thing I want to do is what I promised at the end of last video, showing that isomorphisms preserve the order of an element. So let X have order n, and f of x have order n. So here, f is an isomorphism. Okay. Then f of x to the m is the same thing as f of x, or x to the m, f applied to it. It's hard to distinguish in words, but you see what I've written here. Right? So if we know that the order is m, of course this means that f of x raised to the m power is going to be equal to e prime. And then this power of f of x is the same thing as f of a power of x. Since this is a bijection, we know that x to the m must be the identity. And so m is less than or equal to n. Sorry, greater than or equal to n, right? Because n is the smallest positive integer such that x to the n is equal to the identity. So if x to the m is equal to e, then m must be bigger than or equal to it. Also, since x to the n is identity, f of x to the n, which is f of x to the n, equals f of e, which is e prime. Thus, n is greater than or equal to m, right? Because m is the smallest possible order, or is the smallest possible exponent for x to be equal to, for f of x, sorry. M is the smallest exponent for f of x. So if n is an exponent for f of x, it has to be bigger than or equal to m. And so the only way for both of these equalities to hold simultaneously is for m to equal n. Therefore, if you have an isomorphism, f, then any element x and f of x must have the same order. Okay, so that's all for this video, and I'll see you in the next one.